who here knows what are systematic reviews? Okay. Okay. So if you don't know what are systematic reviews, then you're lucky. Because systematic reviews are a type of clinical research. It's usually done mostly in clinical research, but it's also picking up in other areas, in which your job as a researcher is to find every little piece of evidence or every study that's out there that could answer your question. So basically, it's a very comprehensive and reproducible literature review. Too often than not, you end up having to work through 10,000 articles or so. So the process goes as follows. You put in your research question. You work with a librarian to get together a search strategy in place. You submit that search strategies to various bibliographic databases. You get about 10,000 citations, and then 2 people have to go through each citation, review the screen the article and abstract of the citation against a set of inclusion and exclusion criteria, and decide if this citation should be included, and we should go and hunt for the full text, and then read the full text, and then finally include it in our systematic review. The whole process takes, on average, 2,500 person-hours. It's crazy. It takes sometimes 2 years to publish a systematic review. By the time you finish the systematic review, there are so many new studies out there that whatever you found is outdated and you need to start all over again. So I was first introduced to this torturous process in 2013. And back then I thought, geez, there has to be a better way. We get Google to do a lot of stuff. How come we cannot get this done through some kind of an algorithm? The challenge, the technology wasn't there. So the challenge we have right now in this little first piece of a systematic review process, which is just screening the article, is we need to develop a classification machine learning algorithm that is able to review each article, each abstract, contrast it against a set of inclusion and exclusion criteria, and then decide if this study, basically classify or label the study as included or excluded. No, much better. So the challenge here is this is a problem that is difficult to do in a supervised fashion, because each systematic review is very much different. So collecting a bunch of systematic review, then running an algorithm or training an algorithm on it doesn't really work, because the next systematic review will have unique set of inclusion and exclusion criteria, and it will just not be possible to replicate and generalize models into new systematic reviews. So basically what you need to do is you need to train a machine learning model on each systematic review you're doing. Now the challenge here is that this is an extremely imbalanced classification problem, meaning we end up usually with 2% of the articles that we retrieve from bibliographic databases as included. 98%, this is a huge class imbalance in machine learning. You're almost dealing with an outlier problem now, just compounding how difficult it's going to be. So one, we need to train a machine learning model on each data set. 2, on each systematic review. 2, there's only a very tiny bit of systematic studies that are included. So the existing solutions are called active learning. Active learning, basically, you go into a project and you start doing your own screening. You start reading through all of these titles and abstracts. Okay. And as you're doing it, you're training the machine learning model, and it slowly starts picking up the work on your behalf. Now, the challenge in active learning is you end up screening about 50% of the articles anyway. So, if you get yourself 10,000 articles to screen in a systematic review, you're going to have to do half of the work, and then the machine will take the other half, usually the easy one, not the tricky ones. So come large language model. Oh my God, they can reason, theoretically. We can use them as an unsupervised classification tool to determine if something is included or something is excluded. We have all of these models. We have small models, large models. We have all of these prompting strategies. We have zero shot, few shots, chain of thought. So let's build together an app that can screen articles. So I'll walk you through some of our initial testing of the large language models that we tested. And also, since this is a tutorial, unfortunately, I didn't get the chance to make it a Jupyter notebook. But this should show you, if you're unfamiliar with Streamlit and you're in Python programming, this is an easy, straightforward way to build a large language model application. So we're going to walk through that a bit, and then we're going to look at the results that we got from our testing on a couple of ground truth databases. And I'm hoping you will find it as engaging as I found this whole process. So starting our project, we're looking at first of all, disclaimer, I'm not a software developer. My background is in medicine and epidemiology. So whatever you see here that doesn't adhere to some QA practices, please do. Yeah. Okay, so I usually like, when I'm starting my large language model applications, I usually like to start by defining my base, my base models. We're going to use LangChain here, so we're going to get our environmental variables. I'll be using OpenAI. I'll be using Azure OpenAI as well, because we have some credit there. PS, third-party credits are not supported on Azure. So if you have Azure credit, you can only use them on Microsoft models and on OpenAI. You cannot use them on other models, that third-party models on their Azure AI Studio. We learned this in a very, very, very expensive way. So just so we're going to call in our environmental variable. We're going to start an OpenAI LLM model. We're going to initiate another one for Azure and another one for AWS Bedrock. I have to say, I'm loving Bedrock. I'm sorry, Brett, I didn't try Google stuff, so just so if this is going to sound like an AWS ad, I'm sorry about that, but AWS Bedrock is cool. We're going to try those various models. So in order to be able to call the models without going through a gazillion if statements, we're going to do a model map where each model name within the API call is associated with the model function. So we're looking at all of the major leading ones: Llamas, Mistral, Anthropic, and GPT. And then I have this alias map just to keep my file names short, nothing fancy. So after we defined our base models, I usually like to define the processors. I'm going to skip through the processor specifically for GPT. The only thing different about it is that it will call the JSON object, which I haven't tried yet, the structured format function that they introduced. So basically, this is a function that takes in the model that we just defined and some parameters, including a task prompt or a system prompt, as well as a human prompt, max retries, and the model that we initiated in the beginning. I have a small helper function that retries calling the model if it fails, because we tend to go over our API limit all the time, and I don't want things to crash in the middle. We have some logging here thrown in the middle, and here we have a small trick that we found to be very useful. And by we, I don't mean we as, oh, I'm high almighty. We have a team that's helping me out in a lot of things, so I do want to give them credit. So what we found out is it's easier to get the output in tag format and then extract it from the tags, as opposed to having to wrangle with JSON, give me JSON, and okay, here is your JSON, and then the whole thing crashes. So in our prompts, I will show you in a bit, we ask the output to be done in tags, And I have a small, very easy extract tag function here that will get the content from between those two tags. Some try and accept here, and then we will get the return here. It will return basically the decision whether to include, whether to exclude, and any information that were fed into the model. So let's take a look at the prompts. I like also to have a prompt library separate than actual hard coding into the model that we into the AI caller, largely because it allows us to change the prompt without going through various models and changing them manually. You just cannot keep up. So we have a JSON output prompt that we feed. This is specifically for the ChatGPT one. The human prompt is very easy. Should this study be included in a systematic review? And then we have three types of prompt. We have the chain of thought prompt, and for those who don't know, chain of thought is basically prompting the large language model to reason and give you that reasoning back. So we have a chain of thought prompt, and that chain, the prompt will provide parameters in the inclusion criteria as defined by the researcher, exclusion criteria, title, and abstract. And you tell it what to do, first read through, provide final answer, and here are the parameters that you need. Sorry, I jumped into a different prompt. Here we were talking about putting it in a block. So here, first carefully reason and put it in a reasoning block. And then put your decision, whether true or false in a study included block. That way we could extract those numbers, those tags, without actually having to force a specific structure. We have a small model here, Pydantic model, not super important, honestly, for this application, for this small application, but if you have something bigger, it's really helpful to have the validation that is built into Pydantic. And those are basically our base functions, our base abstracts. And now we can go into the actual AI caller. So we have a chain of thought. The chain of thought, that is the function that will take in the model that we just defined, the title, the abstract, the inclusion criteria, exclusion criteria, and number of retries. And it will basically just call that prompt. I forgot I had some phi models here that I was also playing around with. Not very helpful for this specific task, but perhaps for other tasks. And then we have a similar one for 0 shot and another one for few shots. So 0 shot is basically giving it the title and abstract and asking it, should this be included? No reasoning required. Few shots is basically, here are some examples of some included studies and examples of excluded studies. Please decide on this study. So once we have all of these put together, if you want to put a Streamlit app, which I find it very helpful in many cases, even just for testing. I'm terrible with JavaScript, terrible with front end. I don't understand the difference between CSS and HTML. So this is super helpful for someone who's illiterate in the front end side. So we go with Streamlit. Streamlit has all these little functions that translate into some kind of a front end. So we start with the title, then we define the models, and then we have a drop-down menu for the models and the tool, and then it basically runs. So to start this Streamlit function, here we go, live demo, fingers crossed, Streamlit run. Let's see. Okay. So as you can see, I'm very much not visually inclined. So this is very helpful for me that someone else did all of the heavy lifting here. So we have now a front end that does the task for us. Not really a front end. I know that might be offensive for the actual front end engineers. But we have an interactive platform. So I took the liberty of having something already, damn it, connecting. So I need to copy paste these. So it would be in the form of, let me see if I can get it to reconnect. Rerun. Okay, here we go. So we would be choosing our AI model basically. Let's go with something that is more recent. What would you like? 405B? Yeah, okay. And let's go with chain of thought. Screening. So we have a title, we have an abstract. I took the liberty of putting some inclusion and exclusion criteria for that specific systematic review. You submit, and in the background, I can probably show you the logs. It's basically calling AWS, and it will, 405B is rather slow. Okay, so we have something. So final decision here is false. So it's not to be included, the study, it's excluded. Confidence score is 90. Don't give it too much thought. Confidence score, I haven't fine-tuned on confidence score, but just an idea that you can have that as well. And reasoning summary, I've been in this field for quite a while. This reasoning is amazing. I've seen so many systematic reviews done where there is hardly any reasoning around why we're including and excluding study, that this is actually super helpful. But like any other scientific important domain, we really need to figure out the metrics. How well is this performing? So to do that, we went into something called the synergy dataset. The synergy dataset is a freely available dataset of about 82,000, it's about 170,000 articles from 26 systematic reviews. And as you can see, the highly imbalanced problem, only 1.67 of them are included. All the rest are to be excluded. So, throw in any model and it will give you some amazing accuracy, but is it useful? Not really. So we went into that data set, and unlike all of the other approaches in active learning, in which it doesn't really look into your inclusion and exclusion criteria, it just looks into what you're doing, and then it starts training that machine learning model. Here, you actually need the inclusion and exclusion criteria to feed it to the large language model to make a decision, to reason, if large language model reasonings, to reason over those criteria and to give to pass a decision. Now, the challenge is we needed to go through the systematic reviews that were done here and try and figure out if they have clear inclusion and exclusion criteria or not. So we ended up taking about 3 systematic reviews from this database and putting them in our testing and evaluation script. So in our evaluation script, we have here, let me show you what we did for the data set. So we basically have around 3,975, and basically we have the OpenAlex ID, which is a sort of an ID, so is the DOI. The title, abstract, this is ground truth, false, or false for excluded, true for included. Just to keep a track of the data set, and the inclusion and exclusion criteria. Now these, let's go to our evaluation script. These go into our evaluation script. I will not bore you with a lot of statistical details, but basically the evaluation script takes in these articles and calls in one of the large language models according to the prompting strategies that you want, and gives you a result. And then we have a small evaluation tool that calculates various metrics, and these metrics are, if you remember your biostat class or statistics class, if not, it's probably always useful to refresh on them. So accuracy, precision, recall, F1 beta, and we'll talk about why F1 beta, evaluation matrix, classification matrix, negative predictive value, and positive predictive value. So we measured all of these metrics for each model and for each prompting strategy within each model. Expensive, takes quite a bit of time. We spent quite a bit, we span off several instances. Multi-threading. If there's a batch function, use the batch function. If there's no batch function, then you're kind of stuck to do it one article at a time. But I will take you through the results, so you don't have to wait for 4 or 5 weeks like we did. And the results are very much surprising, I would say. So we're looking first at, how do I make this bigger? Yeah, okay. So let's put one thing out in the clear. Indeed, chain of thought is better than other prompting strategies. And you will find that we're using recall here most often. So at the risk of sounding like your boring statistics professor, does anyone know what is recall? Okay, can someone tell us what is recall? Okay. No worries, I get that all the time. So recall is the percentage or the proportion of actually included articles that the large language identified. So in this data set that we showed you, 3,975 articles, only 81 are actually included. All of the rest are excluded. As we discussed in the beginning, it's super important in systematic review to capture every piece of study out there, because that's the purpose of it. Systematic review. You're reviewing the literature for every and each study out there that answers your question. So the most important metric here is recall. If we have bad recall, then we might as well not use it. So the first metric that we want to rank them on is recall. The second metric that is important is precision. Okay, I'm not going to do it again. I'll just tell you what precision is. Precision is the proportion of the articles that the large language said included that are actually included. What it means. So the large language model returns, let's say, to keep the math simple, 100 articles. And it has perfect recall, meaning it captured those 81 articles. So the precision there is 81%. It retrieved from those 100, 81 of these citations or articles were actually included. So precision is 81%. So that gives you an idea on how much work as a human I would need to do after I run this over with the large language model. How much is going to be left for me to go and grab the full text and start reading the full text and then decide if this is included or not. So with that out of the way, recall, as we are progressing with chain of thought, this is very bad. It's basically dividing by 0, which is very bad, because it didn't capture anything right. Everything was excluded. If anyone from Cohere here, Command R plus is better, definitely. We're looking at few shot and zero shot. For few shots, we use 3. So there's always this kind of, few shot and 3 shots. Sometimes few shot is better, sometimes it's not. So I'm not sure if 3 few shots is sufficient. It might have needed more. But definitely, consistently, we're seeing chain of thought performing better than the other 2. So with that out of the way, I'm not going to look at the results from 0 shot or few shots. We're just going to look at the results from the chain of thought. This is the same case with precision. Precision with chain of thought has always shown a bit higher than 0 shot or few shots. So this is the recall across all of the models. So it goes from 0 to 1, or if you want to call it a percentage, it goes from 0% to 100%. And something interesting you're going to see here, bigger is not always better when it comes to recall. And newer is not always better when it comes to recall, even within the same family. So if you look at Claude 3 Sonnet, it had about 97% or 0.97 recall. 3.5 Sonnet had quite a bit less recall. Same prompt, same data set, same inclusion and exclusion criteria, everything. Similar things we're seeing here, where 4O mini actually has slightly better recall than 4O. But that doesn't tell the whole story, because a model can go in and say, hey, you have 3,975 articles. All of them are included, and it will have a recall of 100%. So that is not the end of the story. Recall is not the end of the story. Another important aspect is precision. And here with precision, we see the highest ranking model in precision at around 26% is Claude 3 Opus. So here you will see bigger achieves better precision. Newer, more or less compared to its own precedent, achieves also better precision. So this is an interesting paradigm in that newer and bigger model, these are both put on top of each other so that you can have the full story. Newer and bigger model tend to I hate to use the word reason, but they tend to reason a bit more than the smaller model, but that also puts them at a more likelihood to exclude something that should be included. And that is not necessarily to say that the model is wrong. In fact, there is human error in ground truth. We just don't know how much is the human error in ground truth. But studies out there put human error around between 5 and 15% in article screening. So looking at this, we want to decide, okay, so what can we use for our application that screens the articles? So let's put things first. It's important to only look at models that achieve high recall. Because again, if you don't capture what needs to be captured, then what are we talking about? So let's filter them out by models that achieve 90% recall. And then we get only two, Sonnet 3 and Llama 3.1 8B. Only those two models had a recall of over 90%, which is something we could justify because, again, we said human error is around 10%. So, if we get a large language model doing the same thing and performing similar or better than humans, but we're gaining so much efficiencies, saving so much time, and actually putting people, graduate students and PhDs, into doing something other than just reading articles over and over and over again, and actually doing something that is getting used, their talent in a good way, then I would say that's a huge win. But in both of them, you will see precision is a bit low. But what does it mean, this precision? In simple words, Sonnet 3 included 929 articles. So it managed to screen out around 80%, which is huge. It's not unusual that a human would reach a similar number, slightly less, but it's not unusual to have that number. Of these that it included, it missed one article. While Llama 3.1 8B, with its, I should probably flip them, but with its low precision, which was around, I think the precision was about 4, it included 2,222 articles, basically almost 50% of the original testing data set. And it missed 7 of these. Now, if I have to retrieve the full text over 2,222 articles, one, I will go bankrupt because they're so freaking expensive in some of those paywalled journals. And two, I will spend quite a bit of time. So this is what it means, basically. And with that, I want to emphasize a few limitations here. One, as I said, there is human error in ground truth. So there might be some articles that were missed by humans in the data set that we use. There might be some articles that were included that were not supposed to be included in the human data set. Now, we're comparing these numbers against the numbers obtained after the researchers have looked into the full text. So the models here at a slight informational disadvantage compared to the humans that we got the ground truth from. And finally, something that is very interesting that I didn't get the chance to test is in-sample versus out-of-sample testing. So this is kind of important, and I don't know how much it affects these results. All of these models have been trained, I can almost guarantee 90% that those articles that we just screened were part of the training corpus for these models. Now, does that bias them? Does that, if we get articles that were not part of the training corpus for this large language model, would we get different results? I don't know. And with that, I hope this was useful, and happy to take any questions.
Thank you. Questions? Yeah, okay. Well, I'll grab this.
Yeah.
All good. Keep that one up. Oh, keep that one up. Yes, good idea.
Okay, first of all, great presentation. Simon, as a software engineer, the code was beautiful.
Thank you.
So my question is here, that you said previously students had to go over and over again through these papers, reading them just for the purpose of finding them. But doing so, they were also like reinforcing the understanding on those papers. Do you think, this is more of an opinion-based question, do you think the increase of reliance on AI, the gradual knowledge of the humans in these specific areas is going to decline, and if so, how would that impact the market or the jobs?
Excellent point. It's I learned quite a bit from doing, this tedious work. But would I have learned more had I not been doing tedious work and doing something else? I don't know. Now, who here knows how to use linear regression? Who here knows how to do it on paper? Okay, quite a bit, but yeah, it's the same concept. We learn linear regression, then we just put the function on whatever software we're using. So same thing, I believe, coming in here. You will learn a lot of these concepts. You will learn, how to read papers, what papers are good, what papers are bad, but then you should more or less expect to spend your time on actually writing and doing papers and research instead of reviewing title and abstracts of other people's research. That's just my thought. But excellent question. Thank you. Yeah, don't focus on the confidence score. That's just an experiment we're doing.
Oh, I was just wanting to know how well calibrated.
Not very well. So that's for the confidence score. Your earlier question was keywords. Yeah. Would they be helpful?
If you just use the dominant thing like
yeah.
Citations.
Yeah. So a lot of the keywords, a lot of the articles that can be filtered out using keywords are kind of already filtered out in the search strategy that the librarian provides. So for example, they will try to filter out any animal studies if you're doing human. So they will remove rats, they will remove dogs, they will remove any cell culture or something of the sort. They will try to exclude anything that doesn't include the drug you're interested in, for example. So a lot of what comes to you on your desk, they all have very similar keywords. In fact, if you would take all of these citations and put them in an embedding vector, they all in a very similar region. it's quite tricky just to rely on keywords, and a lot of reviewers, manual reviewers, will do that. Will put in a keyword, they will highlight the keyword, and they will know that if this keyword exists, then it's not really something they're looking at. For example, if the librarian doesn't filter out based on the study design, and they usually don't do that because filtering out on study design is not very good, so you might end up missing stuff. So when you get, as a reviewer, when you get those articles, you look for the study design that you're interested in, randomized controlled trials, for example. Or you look for study designs is excluded, like case reports, for example. You don't want to include in case reports, so you do a keyword search, and then you get an idea there. But keyword search can take you so far when you're reviewing. A lot of the traditional models depend on the density of specific keywords, but that will always take place after the reviewer active learning, after the reviewer identifies several articles for exclusion and inclusion.
Also, why did you use like a medical, like you have the pre-trained models like MedPowerful and stuff which are trained on bioarchive, like all of those. So I was just curious to know.
Can you repeat the question? Sorry, I didn't.
Oh, just in terms of the large language models that you're using, why do you choose to use like a generic large language model versus something that's trained on MedArchive or?
So the question is, why did we choose the language models we chose? Yeah, there's no specific reason. We chose the ones that were available and were known to be performing good. So we went with Cohere, Mistral, Anthropic, OpenAI. We tested Phi from Microsoft. We tested the Amazon one. I can't remember what's called. So yeah, nothing specific. There's no specific criteria we had in place for large language models. We wanted to test as much as we can get our hands on without having to, train our own, buy GPUs and stuff like that.
Oh no, but I guess I was just curious to know if there would be a difference in performance with medical pre-trained model versus, because you have a bunch of.
I see what you mean. So yes, Google, for example, has the medically trained one. We haven't tried that. I think it's not as easily accessible. If you can get us access, that would be fantastic.
We'll go to our next question.
Great presentation. I kind of have a two-part question. Roughly order of magnitude, how expensive is it to run one of these systemic reviews with an LLM?
So I would say, again, depending on the LLM, GPT-4 or Mini, for example, is very affordable. But Opus, for example, the most expensive one, you're looking at $1 on a citation.
Oh, and citation. Okay.
Yeah.
And then what would be the benefit of using a more broad set of articles or a super human systemic review? Because I imagine there's some initial search that's performed. If you're using an LLM that's so cheap, maybe you can run it on a more broad set of articles.
So the question is this generalizable to other fields beyond clinical research?
More so just, would there be a benefit of running the systemic review on a greater set of articles now that you're not having
Yes.
time to look through it?
Yeah, that's something that actually motivates us. Is a lot of the time there's a back and forth between the librarian and the researchers, because the librarian comes back, here I found 5,000 articles, and the researcher says, oh my God, I'm going to spend my next 5 years doing this. And then they ask the librarian, can you narrow the search strategy? So the librarian works on narrowing the search strategy. So you're absolutely right. If we could automate this, then we could potentially capture more stuff that is traditionally being missed. Yeah.
Take one more question. Yeah.
Hey,
Or two more questions, sure.
that was great. I can see the value. Clearly, you must be working with organizations like Ghayath, right?
Correct. Yes, I worked there for 7 years.
So you know, yeah. So you probably know. I can see the story. How are you deploying some of this to those arms? So I didn't quite get that from what you're showing. So what's the business?
So I didn't want to sell from the stage, but we ended up, we didn't like any of the results that we were seeing. As you can see, the precision for the best performing model, Sonnet, was around 7%. We wanted more. So we actually built our own algorithm that is enabled with large language model. So it's an agentic workflow, multi-agent workflow that follows certain algorithm, and we're achieving a 95%. So we're achieving basically double the numbers of Sonnet. We're achieving 96, 95%. And the precision is double that of Sonnet, easily double that. And we're using that as the step 1 of our automation process for systematic review. Step 2 in the automation is to grab the full text of the stuff that the AI decided to be included based on title and abstract. Now, this requires some manual labor because some of them are behind paywall, and we need to go in manually and buy them. And then we have another screening based on the full text, and then we've built an extensive agentic AI for data extraction that extracts studies based on their design, and then summarizes everything. And the full systematic review that used to take 2,500 hours with validation, with human-in-the-loop validation, takes around 85 hours now. Thanks.
That was a very nice presentation. I guess my question would be on the practical side.
Gotcha.
So how painful was it for you guys to get to the prompt, the correct prompt, to get to the output that you needed? I saw you use a bit of pydantic there, perhaps, for structured output. And then I guess the second part of the question is, as a very technical individual in one field and perhaps a little less on the coding side, would a no-code tool that allows you to chain prompt like this help you a lot, and would you use it under what conditions?
Yeah. At the risk of sounding like another ad for AWS, they have an interesting tool called Party Rock. If you haven't tried it, try it. It's a no-code tool that allows you to chain prompt and make an app based on those chained prompts. It's called Party Rock. It's very good for a lot of different potential simple uses of large language model enabled applications. So yes, a no-code chain tool can be helpful in this case. Getting a Streamlit app is not too difficult at all. In fact, go to your favorite AI and ask it to spin up a Streamlit app based on your functions, and it will do that. It's not very complicated, and you can actually host the Streamlit app and deploy it on the Streamlit servers. So this is another easy way to get your app out there and try it out before you commit any significant amount of additional resources on it. Did that answer your question, or did I miss something? Right, prompt engineering. I was also in the camp that prompt engineers are the next data scientists until Anthropic came with their prompt generation tool. That is not to say it captures everything, but the only way for you to arrive at the appropriate prompt or in context learning is through not necessarily just trial and error. You need to have some metric to decide if you're doing good or bad. For example, for us, we're going with the F-beta score. F-beta score is basically the recall as well as the precision, with more emphasis on the recall. And we kept on trying different prompt strategies until we reached a point of diminishing return. And we said, okay, that's it. So there's no more we can do on that front. So whatever you're doing as a large language model enabled application, you must have that metric of evaluation. Otherwise, you're just shooting in the dark, basically.
Thank you.
Thank you.